The engineering community is very lazy, especially with acronyms. Like, every name for anything ever is usually reduced to an acronym. And for beginners, this can be very confusing. So today, I'll be giving a short introduction to networking and attempt to clear up any confusion by explaining each concept through the definitions of the acronyms. Let's get started. First up is a LAN, which is short for Local Area Network. Anyone who has played Minecraft has probably seen the Open to LAN button, which allows other people connected to your local network, such as those on your home Wi-Fi, to join the game. One way to create your own LAN is through hardwired Ethernet cables between machines. This can be direct, although it is typically done through a center point, such as through a switch or a hub. LANs technically do not require internet access to exist and therefore don't need a router. However, a typical home LAN is often connected through Wi-Fi, which is provided by a router. This is known as a WLAN, or wireless LAN, as it relies on wireless protocols such as Wi-Fi to transmit data. Not to be confused with a WLAN, a WAN is a wide area network and connects multiple local area networks to each other, often over large distances. A WAN can consist of a network over a city, a country, or in the case of the internet, the entire world. WANs may also be private, as companies often have their own private network consisting of multiple LANs. Next up is the OSI model, which is short for Open Systems Interconnection. This model is a conceptual framework used to standardize and describe how different networking systems communicate with each other. The model consists of 7 layers. The top layer is the application layer, then followed by the presentation, session, transport, network, data link, and physical layers. Each layer in the OSI model represents a specific stage in the process of transmitting or receiving data, with specific protocols associated with each layer, most of which are also represented by acronyms. As a quick side note, there is a predecessor to the OSI model, known as the TCP/IP stack, which has 4 layers rather than 7. In this model, the application, presentation, and session layer of the OSI model are combined into a single application layer, while the data link and physical layer of the OSI model combine into just the link layer. You may also see the network layer be referred to as the internet layer or IP layer. And as a disclaimer, despite the name TCP/IP stack, the model itself is not the TCP or IP protocols. We'll talk about those in a little bit. Moving on, let's talk about individual layers from the bottom up. The physical layer is in charge of transmitting and receiving the actual ones and zeros over a medium, such as a wire, and has protocols like Ethernet, Wi-Fi, USB, Bluetooth, and so on. If you wanted to implement Ethernet, for example, you would most likely use an Ethernet PHY, which is short for Physical Layer Transceiver, and is a circuit designed to handle the physical signals and communicate with the link layer. Speaking of the link layer, it's responsible for packaging the communication on the physical link between 2 machines into what are known as frames. The data link layer is often split into 2 sublayers. The upper layer is the LLC, or Logical Link Control. This part handles flow control, acknowledgements, and error correction, but only between 2 devices that are directly connected. This is different from higher layers, which considers communication across an entire network. The lower layer is the MAC, or Media Access Control sublayer. If you've ever heard of a MAC address, this is where they come into play. MAC addresses are used to identify devices at the hardware level so they can communicate over a local link. The device you're using to watch this video is most likely connected through Wi-Fi and will use MAC addresses to communicate directly to your router over the wireless link. Above the link layer is the network layer, which also plays a major role in addressing. This layer is where IP, or Internet Protocol, lives. IP, like MAC, has addresses that are used for identifying machines. The difference between the two is that while MAC addresses are used for direct local communication, IP addresses are used for end-to-end communication across multiple networks. The most common internet protocols are IPv4 and IPv6. I won't go into full detail on how they work, but for those curious, here's what an IPv4 packet looks like at the bit level. If you send a sequence of bits that follow this format, a tool like Wireshark or TCP/dump can recognize it as an IPv4 packet and extract the data inside. IPv4 addresses are 4 bytes long and often written as 4 decimal numbers, each ranging from 0 to 255. This gives a theoretical total of over 4 billion unique addresses. You may be wondering how 4 billion addresses is enough when there are clearly more than 4 billion devices in the world today. That's why IPv6 was invented. It uses 16-byte addresses, often represented in hexadecimal, which allows for an unimaginably large number of unique addresses. However, IPv6 hasn't really taken off in the way you'd expect. You may notice that most IP addresses nowadays are actually still IPv4 addresses. This is largely due to DHCP, or Dynamic Host Configuration Protocol, which allows IP addresses to be reused by assigning them temporarily. Combined with NAT, or Network Address Translation, which lets an entire local network share a single public IP address, these technologies can extend the life of IPv4 far beyond what was originally anticipated. There is one issue with Internet Protocol. It doesn't provide a reliable connection between two devices. Packets are simply sent blindly, meaning data can get lost or arrive out of order, or even be corrupted. To solve this, the next layer in the OSI model, the transport layer, introduces protocols like TCP, or Transmission Control Protocol, which is arguably one of the most important protocols on the entirety of the internet. TCP is responsible for establishing a connection between two endpoints and ensuring that the data is delivered reliably and in order. This connection starts with what's known as a three-way handshake, where both sides agree to begin communication and a connection is established. Once a connection is established, the sender can begin transmitting packets, and TCP takes care of making sure they arrive correctly. If any packets are lost, TCP will automatically detect that and then retransmit them. TCP also introduces the concept of ports, which are essential for directing traffic to the correct application on a device. These aren't physical ports like a USB port or an Ethernet port on your computer. They're virtual addresses used by your computer's networking stack to decide which application should handle the incoming data. With over 65,536 possible ports, this system allows many different services to run simultaneously on a single machine. Before we move on to the next layers, I want to clarify what a packet really is and how it gets built as it travels down the layers of the OSI model. If you've ever seen, given, or been given one of those prank gifts that's like a box, like many gifts are, but when that box is opened, there exists another box inside of the first box, and then another box inside of that one, until so on eventually the gift is finally retrieved. Well, that's basically what a packet is, where the actual gift is the data intended for the application, and each of the boxes are the protocols that wrap around it at each layer. For example, let's say we are sending a message to our friend over Discord. This message will use TCP as the transport protocol, IPv4 for network addressing, MAC addresses for the data link, and Wi-Fi as the physical transmission method. Our message traverses the protocols top-down, so first, at the transport layer, the TCP header is added around the application data. This includes source and destination port numbers to help identify which app the data belongs to. Next, the network layer adds an IPv4 header, which contains the source and destination IP addresses so the data knows where to go across the internet. Then, the data link layer, which in this case uses Wi-Fi, adds a MAC header, specifying the source and destination MAC addresses for local delivery within the local area network. Finally, at the physical layer, the entire packet is transmitted wirelessly as a stream of bits over the air. On the receiving end, the process happens in reverse. Each layer will remove its respective header, passing the payload up the stack, until eventually the original message is all that's left. Now that you understand how the internet transfers information, let's shift back to the upper layers of the OSI model. If you recall, the top three layers of the OSI model are collapsed into a single application layer in the TCP/IP model. The session and presentation layers in the OSI model are mostly theoretical, and not many real-world protocols fit in them perfectly. So I'll do my best to give protocols that somewhat belong in each layer, but generally it's better to think of these protocols as simply application layer protocols. The fifth layer is the session layer. A session is an ongoing conversation between a client and a server. An example of a session-like protocol is TLS, or Transport Layer Security. This protocol used to be known as Secure Sockets Layer, so often you'll see TLS/SSL. TLS can be used to create connections which are encrypted, and thus safe to send over the internet. This protocol is why you are able to send sensitive information, such as your credit card, through the internet without anyone else being able to read it. Moving on to the presentation layer, this layer ensures that data is translated into a format that can be understood across different systems. It takes care of tasks like character encoding, such as ASCII versus Unicode, by order translation, and data compression. A well-known example of a presentation layer standard is MIME, or Multi-Purpose Internet Mail Extensions. Many email systems were originally designed to only handle simple text, but MIME makes it possible to send and correctly interpret more complex content, such as documents, images, and even entire web pages. The final layer is the application layer. This is where real-world network interactions happen. It's responsible for the actual software interfaces that allow programs to communicate over the network. In fact, an application layer protocol is responsible for giving you this video, known as HTTP, or Hypertext Transfer Protocol. HTTP is what allows your browser to request and load web pages from a server. And when that connection needs to be secure and authentic, such as if you're making an Amazon purchase, HTTPS is used, which is just HTTP running over TLS, a protocol you are already familiar with from the session layer. For the final part of this video, I'd like to answer how standards and protocols like HTTPS were actually created. Protocols on the internet don't just magically exist. They are formally specified by organizations such as the IETF, or Internet Engineering Task Force. The IETF publishes documents known as Request for Comments, or RFCs. Despite the informal name, these are official technical documents that define how protocols, architectures, and technologies should work on the internet. Each RFC gets a unique number. For example, RFC 9293 is the most recent official specification for TCP as of making this video. There have been many older RFCs that specified TCP in the past, but they are now considered outdated or deprecated. So the next time you're using a web browser, sending a message, or loading a video, you're actually relying on thousands of pages of carefully written RFCs to make it possible. Hopefully you now understand how the internet works just a little bit better. So thank you for watching, and I'll see you next time.